Good morning.
Hi, Michael.
How are you doing, Jan?
Doing well. What about you?
Quite well indeed. Yeah, didn't get too much dev work done on Jinaga.net this weekend, but um, excited to see what you've been able to accomplish.
I adapted the drawing, but not much more than that. Yeah, I've sent you a link via the communication channel of the book club.
All right,
But,
pulling that up now.
I saw your video about the .NET Interactive Notebook,
Mm-hmm.
and that was really nice. The rendering.
Yeah, I found that to be pretty useful. So, so yeah, it's basically given me a way to think through um, what kind of models I want to support, and then I'm able to take that code, put it into unit tests, and start making them actually work. So that's the part that I'm on now, is the actually work part.
By the way, Michael, are you hearing some noise in the background? Because I have a fan on here.
No,
Um,
it's getting filtered out quite nicely. There seems to
okay,
be a noise floor, so after you get um, below a certain level, then I'm not hearing anything.
I can leave the fan on. Otherwise, I have to
No,
switch on the
that's
airco.
yeah,
It's
that's fine.
getting too hot if I close the door. Um, do you see the picture?
Yes, I do.
Okay, so I reorganized it a little bit.
Mm-hmm.
I took in account the remarks you gave me last time. So okay, here we have the four comments actually: subscribe, watch, query, and and effect.
Mm-hmm.
So if you add effect, it goes to the memory store, which stores it locally, which sends it to a queue, and the queue will try to save it into the server, going through the authorization rules, which are still coming.
Mm-hmm.
If you make a query, it will go to the pipeline compiler, the local store, and it will get a single answer back. Watch is doing the same thing, but uses the pipeline inverter to get multiple replies every time something changes in the
Mm-hmm.
local store. But that means if something, no, let's put it this way: if you subscribe, then he will simply send the pipeline through to the server,
Mm-hmm.
and the pipeline will send the server will send results back to the local store, but then they will only be displayed if there is a watch active, I guess.
That's correct. Yes.
Yeah. So, and if you have a watch without a subscribe, then what will happen? You will only get local changes.
That's right. Yes.
Okay. Um, and to take into account the compatibility between .NET and JS. So I mentioned both the JS server, .NET server, up and running for JS, for .NET coming soon. For the client, yeah, an empty client, but up and running, which is in fact the same as what we have
Uh-huh.
here. Yeah. And so now everything goes through the fact manager. So I turned it around a little bit, but I think this is more easy to understand.
Yes. Yeah. That's incredibly accurate. I love how um, it's showing the roadmap and the progress along that roadmap all in one picture. So um, yeah, and That is, yeah, that is precisely accurate.
So if you want, you can take it up
Mm-hmm.
on the website. I think if you on top you have a dustbin, then a folder open, then an export, and then save as image.
Mm-hmm.
Yeah, if you click save as image, you can save it as PNG or as an SVG. And you can do it with a background or without background.
Nice.
And you can even save the scale.
Okay, and it looks like it even has embed codes. Uh, Okay, so no, that's not embed codes as in, yeah, that would be kind of cool if there was an embed code on the Jinaga.net or Jinaga.com site. Actually, Jinaga.net exists now, and it points to Jinaga.com. Um, it would be cool if there was an embed there that, as we updated the diagram, it updated the site. But that on second thought, that's probably not a not a good idea. We want to be able to work on this and then decide when to publish. Awesome. Okay, so I'm going to pull this down into the project. Oh. No? Oh, okay. Yeah. Yeah, I'm working on the website on WSL, so I'll pull it down onto my desktop and then move it over. Awesome.
You would want to put it on the website jinaga.com?
Yes. Yeah, I want people to be able to not only get an overview of how the system works, but also the roadmap and the progress toward that. So I think this this is really good support there. Yeah, I on the one hand, I do want people to just be able to use the library and not have to think about all of the infrastructure that's going on. But then on the other hand, I know myself and I know people who consume libraries are like, well, it looks like magic. I don't like it. And so I was like, nope, there's no magic. So this is everything that's going on.
Mm-hmm.
Yeah. So then, yeah, I can put together some documentation describing everything that goes through this in Markdown, and then have a page that is dedicated to the infrastructure and the roadmap.
If you the button on the left of the save button is the export button.
Mm-hmm.
Then you have the original file, the source code for this drawing, let's say.
Okay, cool. So the shareable link is what you just did today. Save to disk.
Yeah, but that link, I don't think that's something that you can use afterwards. Once I stop the session, you don't have, or it will last for 14 days or something. I don't know. But if you just do export, then you have the source file, and you can open that source file again with Excalidraw, with the website. That's the icon to the left of it, load a file. Mm-hmm. Then you have the same file again.
Okay. Yeah.
I think that file should be put in GitHub as well, I think.
Yes. Absolutely. Awesome. Yeah, and then we can go back to that and update it as things change. Yeah, one of the things that I would really like to be able to do is to take this query all out of the diagram, because everything is supposed to just go through query all. It's just right now. Yeah, I started with query, and then later realized that it needed to be more generic, and I just haven't gone back through all the other calls to query to make them calls to query all. But yeah, once I do that, then we can take query all off the diagram, and that's just how you do queries.
Because the j.query will also go through query all then.
Yes. Yeah. Yeah. The all portion of it really doesn't have to do with being able to get subsequent results. The all has to do with getting well, goodness, what does it have to do with again? I think it has to do with the Cartesian product idea. Yeah. So originally, Jinaga.net pipelines were just about the same as Jinaga.js pipelines, but then So first, the first innovation is that I realized that in Jinaga.js, every pipeline is linear, and I needed to support branching. So you could have projections, and you could have inverses that talk about not only the added but also the affected sets. So both of those, and so then I further generalized that idea into the idea of returning Cartesian products, and so that changed the signature of query, and so I needed that first when getting watch to work, but now I can go back and get j.query to have the same capabilities, and also to just go through the same more generic endpoint.
We have save for facts and query for all the queries.
Yes. All right. Yeah, I'll probably when I do that, rename query all back to query, because we don't have to maintain backward compatibility on store implementations quite yet. Once we have multiple plugins, then it becomes important to maintain that backward compatibility. But so far, that's not a concern.
Good. So you got the export as well?
Yes. Yeah, I grabbed the export. So yeah, I've got the file that I can play with.
This session, I think, of the program, unless you want to add something to it.
No, I think I think the next step is to create the markdown file so that we can upload that to jinaga.com and have it available up there, and then get these two files into the repository. Yeah.
Session will override your previous local store drawing. Keep close if you want to keep. Yeah, that's okay. Okay. All right. So that's all.
Cool. Now I did find the diagram that talks about the Cartesian products. So yeah, we can go through that and make sure that you see what that idea is as you get into doing the SQLite implementation. Because that's going to be.
I was wondering about it.
Yeah.
Because a couple of weeks ago you were so enthusiastic about it. Say, yeah, it's all met, and I found the solution. And then the week after, when I asked about it, you said, I didn't say anything. I was wondering, where is that gone? But okay,
Yep.
you found it back.
Yes, I did. Yeah.
Yeah.
Okay. So and now we have this diagram. So imagine that you've got a model, and these are the different facts within the model, and the letters that you see there are the roles. So so I just abbreviated the roles, but they could be things like the conference, the speaker, the creator, the session. So those are all pointing up to their predecessors. And you you start the query at a certain point A, and you want to find all the facts B. So there are a few different paths you can take through the graph in order to get there, and so the query syntax really just describes that path. And so let's suppose that you pick this one. So you say from A, I want to go up to my successor via the R role, and then down to successors via S, and then T, and then predecessor, I said the wrong word before, predecessor U, and then successor U. Interesting thing here, these two roles have the same name. That's going to be quite common in a model, but they're defined by two different facts. So it's really the type of this fact that's in the successor position and the name of the role that make that role unique. So so it could be that that up here this is a user, and so V is the word user in both those cases, but maybe this is a conference organizer user, and this is a speaker user. So each one defines that user role in its own way, and so those are unique, but I still use the same role name within the model. So
for example, you have a school, and the school has teachers, and the school has students.
Mm-hmm. Right. Yeah. So teacher, school.
Teacher points up to a school, and the student also points up to the school.
Yes, exactly. Okay. Yeah, and so this might be the student registration in a class, and this might be the student's name. And so it's like you're like maybe here's we're stretching this, but it's actually kind of working. So yeah, there's the teacher, and so they're part of a department which offers a class. So now for this class in that department, give me all the teachers and all of the offerings that they are teaching, and then all of the students in those offerings, and then the names of those students. So kind of taking this circuitous route to get to just give me the names of all the students in this particular department. And so you would need, in order to define that path, you would need to identify a new fact right here. You'd have to give that a label, so that occurs in linq just to be able to support this syntax. So now in linq you can say you're starting with given A, given that department, do a match of department comma facts, and now facts of type C, of type enrollment, where A.R is equal to C.T.S. So you're able to identify this one by the chain of roles from those labeled facts, and so this part of the where clause, that join, defines this path from A to C, because they have a common ancestor at some point. But then in order to continue on to B, you have to do another join, C.U is equal to B.U. And so at first it was just, okay, I have to label C because that's what the linq syntax forces me to do. Without labeling C, I couldn't I couldn't name these roles. I couldn't say anything about what fact has a T and a U. But I don't have to name these intermediaries because they get an indirect name. This one is C.T. That one is both C.T.S and A.R. So at first it was just, hey, neat coincidence. Or neat observation. And then it became a coincidence when I noticed that the ones that you have to label are also the ones that are at the valley of this zigzag. And that's precisely the same pattern that I noticed in the book when talking about optimizing the inversions. So if you learn about one of these facts, then it's not going to have any effect on this query because it can't yet have any successors. So this one doesn't yet exist.
Yeah.
If you learn about this one, then it can affect the query. So B can already exist and A can already exist. And so now that this brand new C has come into existence, that completes this path. So the labeled nodes, the ones at the valleys of the zigzag, are also the ones that can complete a path. And so they're the ones that you have to start your inverses from. So I thought that was a pretty neat coincidence. So yeah, where at first I was using these labels and taking them from the linq syntax in order to just describe the pipeline so that the pipeline would be human readable. Now I noticed that the way in which I was describing the pipeline was actually useful for computing the inverse. So now in order to compute the inverse, I can just observe that besides the starting point, there are two additional labeled facts, C and B. And so that means I have two inverses. One that starts at B and then follows B.U equals C.U, and then from C goes C.T.S is equal to A.R. And so that takes us, once we learn about B for the first time, that means, okay, A was affected, and B is a new result. And so that's one inverse starting at B, but the other inverse starts at C, and that's the one that follows C.T.S equal to A.R in order to get back to A, and then C.U equal B.U in order to get back to B. So learning about C tells us that that now this path exists. So so that gave me a really nice mechanical way of inverting a query just from the way that I had already chosen to describe it. So I had to change my data structure a little bit in order to make that easier to do as an operation. But yeah, that work has already been done, and that all the refactoring of that code and the unit tests to make them all pass again, that's all working. So then I took one step back from this and made one further observation that I think really kind of blows the whole thing open. And that observation is that this triple ABC, if you think of that as a set of facts, there is an exact instance of A and an exact instance of B and an exact instance of C. So a specific department, a specific student name, and a specific enrollment. Those are consistent. So by just declaring that this is an A, this is a B, this is a C, I'm saying that now this full path exists, and this query is satisfied for that path. So I've got this consistent tuple of facts, and So what I'm looking for when I start with A, and I want to find all of the B's. I start with the department, and I want to find all the student names. I'm looking for the Cartesian product of A, B, C, where A, B, and C are all consistent with one another, according to these paths. And so then, when I compute this inverse, and I know about B, I'm doing the exact same thing. I'm looking for all the tuples A, B, C, the Cartesian product, where now I'm holding B fixed, and A, B, and C are consistent. So I could, in fact, just look at it as given the entire world graph. Here are, this relationship here defines a Cartesian product of consistent tuples. I just get to pick how many of those I want to hold fixed. Do I want to hold A fixed and look for the B and C, or do I want to hold B fixed and look for the A and C? Or do I perhaps want to hold two of them fixed and just look for the third? That's an operation I've not been able to do before, but it's a pretty powerful operation. Haven't animated from this point forward, but let's suppose that I've got this other fact here that I want to label D in order to have an existential condition on it. So I'm looking for these D's. So in our example, this is the student. So where not exists, the student is expelled. So that's the expulsion. So now in order to express that in linq, I have to give D a label. There's no way for me to, is there? Wait a minute. No, there is a way for me in linq to have that not exist without actually giving it a label, because I can just call it c.u. Or I could even call it b.u. Whichever one is more convenient. I would probably call it c.u if I'm coming from A. But nevertheless, the query compiler, or the pipeline compiler, when it sees that you are doing an existential condition like that, then it can say, okay, I need to apply a label here. In fact, right now, the label that it applies, if you don't actually explicitly give it a label, is it uses the role name U. That seems to be a pretty good placeholder for most cases. And so now the Cartesian product is ABCD. And so if you discover a new fact here that causes D not to be returned from that query anymore, now you can remove all of the results from that Cartesian product where D is that particular value.
In software.
Yeah. So
because you still have to run through the graph.
Yeah. So that's the thing. I was analyzing the graph from the perspective of the software initially. So right off the bat, I took the factual and turned it into a pipeline that was a series of steps. And so very literally, you could imagine a machine executing those steps, and each part along the way, it would produce more sets. So starting with A, you've got a starting set that only contains A, and then you take in this role R, and R might be a singular or it might be a multiple predecessor. Either way, you've got now a set of everything that was in the first set followed by this predecessor step of R, and that gives you the second set. And then now you take that and you get, you follow the successor step along the rule S in order to find the set of all things that could be E in this case. And so you just keep on applying these pipeline steps to these sets and work your way from A all the way to B. But yeah, so that was a great mechanism for implementing a pipeline, but it was hiding I mean, first of all, the optimizations that you could do, but then secondly, the beautiful mathematics of how these Cartesian products are related to one another. And it's because it was hiding that, it took away one of the capabilities that I think we can really benefit from, and that's being able to start at multiple places. So yeah, instead, if you just continue to analyze it from the perspective of a Cartesian products, you haven't yet gotten to something that a machine can easily implement. So you just keep analyzing it from that perspective until you get to a point where you say, okay, I really want to execute this one, and then you turn that back into a series of steps. Like, for example, in this case, you've got these two sets of paths are exactly equivalent. The equals operator is commutative. So AR equals CTS, CTS equal AR, same thing. And the AND operator between paths is also commutative. So it doesn't matter that I've done these in this order while I'm talking about just the truth of the statement. But the execution of the statement is very different. So here I know A because that was my starting point, and then I can follow this path in order to find all C that satisfy it. So when I take this and turn it back into something that a system can execute, then I'm doing a predecessor step here, and then successor steps backwards. So successor S, T, and then finally down to C.
Get to C, yeah.
So so you'll see that when this statement is turned into a pipeline data structure, that's when it actually has a list of predecessor steps and a list of successor steps, and it puts them in the right order to be executed. But it's really easy to take that path and flip it around. Take all of these successor steps and reverse that list and make them predecessor steps, and then take the predecessor steps, reverse it, and make those successor steps. And so that turns this into that. So so the second thing about the order of the paths is when writing out the order of the paths to this data structure, I can make the assumption that the starting point for the next path that I'm about to visit has already been established. So here I know this starting point C, somewhere up here, something has gotten me to C. And so that's why here, when taking the inverse starting from B, I flip those two around, and so put B.U equals C.U at the top, so that that gets me to C before I need it here to go from C to A. And for this one, it doesn't matter which order I put those in. I'm starting at C. So I can take C to get to A, take C to get to B, and those two paths are independent of one another. So the really cool thing is in SQL, the structured query language actually stops right here. SQL lets you have a where clause that that takes the product of two joins and makes them equal to each other, and it's the job of SQL to determine how much information it knows, how much is defined by the other steps of the query and how to use the indexes in order to most efficiently achieve those steps. So in SQL, if you if you aren't careful and you don't have indexes in all the right places, then it'll just do table scans and try to find everything that satisfies these equations, and it's not concerned about inverting things. But if you're careful and you put indexes in all the right places, then it can turn this one statement into 3 different query plans based on the final where clause. Are you saying where a.id is equal to this, or are you saying b.id or c.id? And so now taking that into account, it says, oh, okay, you've already fixed the ID of C. So now I can interpret this first line as following this index and this index, and then doing an index scan in order to get to A. So so SQL will actually do the query inversion as it computes the query plan, because SQL works with Cartesian products and tuples. And so that's what I was getting really excited about a couple of weeks ago when I was, or 3 weeks ago now, when I was talking about that this is just relational algebra. It's just what EFCOD was talking about the whole time.
So actually, if we work in the same way as SQL, the SQL engine does in the background, then we could solve this problem.
Yes. Yes, exactly. So the work that the query inverter is doing in order to reorder these paths and flip them around is completely unnecessary for SQL. We're going to produce a different set of structured query language, and then it's going to take a look at it and say, well, okay, I know how to optimize this. Thank you for putting it in the right order for me, but you didn't have to. When it comes to the in-memory implementation, then yes, it absolutely has to be in the right order, because the in-memory implementation doesn't have a
SQL engine.
Yeah, it doesn't create a query plan. So this idea about starting from multiple places. So one of the things that kind of bugged me about using Jinaga.js on a real project is that it has the built-in limitation that every query, every specification really starts at a single point. And so let's take this example where I'm a student, so I'm logged into to my system. Well, I can run a single query from there to find out my name and display that on the screen. That's not a problem. But when I navigate to a particular department, I want to see all of the classes in that department that I'm enrolled in. So that means I either have to run this query, just find everything that I'm enrolled in, and then once it's in memory, filter it to only those things in this department. So do that part of the join after Jinaga is done with it. Or I have to say start with that department and find me everybody who's enrolled, and then filter out everybody who's not me, which is a very silly way of doing that. But both of those would be equally likely, and you don't have to, or you have to choose one of those two when you're actually writing the implementation. So that made the projections in Jinaga.js a bit cumbersome when it got to those contextual type of queries. It's like, I'm a user in a context, so I want both of those things to be my starting points. So now that we can express this as just a set of paths, with labeled facts, and the idea is that it gives you back these Cartesian products. Then here we've labeled A, C, D, or A, B, C, and D, and I say, all right, given A and D, given these two, find me all of the C's. Yeah, and actually in that case, I didn't care about the B's. There was another query over there that gave me my name, but now it's the same set of steps, but two things are given, and so whenever I've got two paths, so the way that would let's see, the way that would appear, let me just duplicate that, is yeah, so we're not talking about this one quite yet. Let's is I've got A and D, so so yeah, this path is true, and then C.U equals D. So I would flip that around. I would write that as D is equal to C.U. Not as an application developer writing the linq, but as the compiler, knowing that, hey, you are given A and D, so I'm going to express them in this order. So now starting with A, I can get a set of C's by following that path. Starting with D, I can get a set of C's by following that path. And then what this what the fact that these two paths exist in the same pipeline tells us is that what we want is the intersection of those two sets of C's. And that's how we compute our Cartesian product of the A, C, and D.
So that intersection is the link between A and D.
Right, yes.
Yeah, that's the common part between them.
Yep. So there's an implicit AND built into to all of these things, which makes sense when you think about these as being a consistent set, that there is an A, C, and D, such that these two things are true. Well, that's what AND means. And so now that's where the query engine, the execution plan builder, comes into play, and then it has to make a decision: which of the two do I compute first? It wants to compute the smaller set first, and then filter it by going in the opposite direction. So it wants to compute DC, and then follow C back to A, and if you get to the correct A, then keep it. If you, since A was the thing that was given and the thing that you want to pin, if you get to a different A, then you throw away that that Cartesian product. And so that would be equivalent to telling the runtime, not the application developer, but tell the runtime to look for all of the classes that I'm enrolled in personally first, and then filter out so that I get just the ones that are in this particular department. And in order for a query plan builder to do that, it needs to use statistics. So that's what the whole refresh statistics is all about. So so that means that either we rely upon the query builder of the SQL engine. So in the case of something like Postgres or MS SQL, we can rely upon those statistics to give us the optimal query, and it's like, okay, let it do its job. Or we capture the statistics ourselves and do that before we give it to the store. So if we wanted to make an efficient in-memory store, then the in-memory store would have to gather statistics. Now, I don't think that we do need to make an efficient in-memory store, so So we'll just let it pick either path and do the right thing. So SQLite, I think it does the statistics thing as well, but that's something that we'll have to investigate. And when it computes statistics, is it just at the level of a particular relationship between tables has so many objects in it? If it's just at that level, which actually might be the case for SQL Server and for Postgres as well, then the statistics aren't going to do you very much good, because all of these relationships are captured in the same couple of tables. I mean, it's really the edge table that you keep on joining to. You just want to know that there are a lot fewer of these edges than there are of these edges. So it might actually take, well, yeah, two options here.
Is it not the other way around?
Yeah, so given a student, the student is enrolled in a lot fewer classes than there are enrollments in an entire department. So yeah, it's the product of R, S, and T in order to get to C. That is much larger, because that's, for an entire department, you've got a lot more enrollments. The student, even though they're enrolled in classes in different departments, they on aggregate have fewer enrollments scoped to the student than there are scoped to any particular department.
Yeah.
So yeah, it could be that that we try to keep all those statistics up to date and infer what is the best query in the model, or it could be that we let the application developer do that for us. So for the most part, I've been trying to avoid putting optimization decisions on the app developer. So for the most part, if you can do something in Jinaga, then it's going to be efficient. That's why it's so constrained. One of the reasons it's so constrained. Like, you can't just query by a field of a fact, because fields aren't indexed, and that's not going to be efficient. You have to query by instances of facts, and so you have to build your indexes into your facts themselves. You have to build those into the model. But yeah, in this case, maybe it's when you express the pipeline. So you say, given a department and a student, then find all these enrollments. As an app developer, you get to choose which of those two you put first. So maybe we say, okay, put the most descriptive one first. So put the student first, and then the department. And so that way, whenever we find ourselves making a decision like this, we say, okay, we're going to take the descriptive one first. And then just keep that information in the pipeline so that as we compute inverses, we still know which one was more descriptive. Yeah, I don't mind that.
If we put the statistics inside Jinaga, then it becomes easy for the user, a little bit like SQL Server does. Usually, you don't really go into the execution plan.
Yeah.
Unless it's really critical, or if it really gets it wrong. Most of the time, it does quite a good job itself.
Yeah. Yeah, and that's the thing. When it gets it wrong, you've got options. You can rewrite your query. You can put query hints in there. You can create indexes that weren't there before. And in Jinaga, you don't have those capabilities. I guess you could rewrite the query, but if the query results in the same set of paths, then it ends up doing the same thing anyway. And you can't define your own indexes. You have to restructure the model in order to index something. Yeah, and it's... Yeah, so it might be... Well, certainly for right now, because capturing those statistics is going to be work. In order to get something out, we can put the statistics lower on the backlog, and take the order.
I'm back.
There he is. Yeah, I was thinking certainly for right now, because statistics would be a difficult thing to implement. We can put those lower on the backlog and just take the order as good enough. And then if we determine that we want to put statistics back in, and that way people can just express the query in either order, and it chooses the better of the two, then yeah, that can be an enhancement for the future.
In fact, Jinaga and SQL are merging.
Yeah.
Coming together.
Yeah. Yeah. So then there's one more thing that that being able to to look at this as Cartesian products, and now that we've got this idea that you're going to do this at intersection anytime you see two paths. So there's an implicit and. That means that you can, if you've got a mutable property, like here, let's say that E is a mutable property of everything. It wouldn't typically have other kinds of successors if it's mutable property, but just go with it. So we've got this self-reference, so the prior list. So it's not self-referential in terms of the instances, but in terms of the types. So now you are looking for, let's suppose that you're, let's say you're just starting a day, a.r, and so now you're looking for e.s, and then here you're saying that where there does not exist a prior, and that would actually get a different label. Since I've already used that circle in the diagram, I'll just call it E prime. But when you're actually writing the SQL, you get to define a new variable for that. So you've got facts of type E that you would call name, and then you would another one, facts of type E, that you would call next. So so there does not exist an E. I hear you. Such that
it's the successor of E dot.
Yeah.
E dot S. No.
Yeah, something like that. So there does not exist an E such that, or an E prime, such that E prime dot prior is equal to E. I see you. Do you want up? No? Okay. So
okay, E prime. Okay, so that yeah, okay.
Okay.
There is not a successor, so that the successor points to
good.
the previous one. Yeah.
Yeah, I still have this up. Awesome. One advantage of going into the office is that this machine retains its state from 1 week to the next. So yeah, I still have this this diagram up. So yeah, in this case, so here I'm looking for the, in fact, I can see it right here, for the name, where name conference is equal to conference, and then this name is current is the not exists. So if I take a look at where is current is defined, so there does not exist a next. And so this is where I was saying you get to give it a new label. I gave it the label next. Where next prior contains this. So yeah, I'm looking for this one here that's highlighted. So there does not exist anything that points to it as prior.
Yeah.
But there's one more constraint that I really want to be able to put on this that so far I haven't been able to put on it. So that constraint should go up here. I should be able to say where next dot conference is equal to this dot conference. So if you take a look at that in this diagram here, you can see that every single one of these in the tree has a pointer back to this same conference, which is what you would typically do in the mutable property pattern. But without that constraint, there's nothing in the query or in the model in general that prevents you from doing that. So you could have a conference name that points back to this one as a prior, but its conference is a completely different conference. It wouldn't make any sense, but that's a fact that you could record. And I think in the book I try to solve that with validation rules. I didn't give those too much of a mention, but that's kind of like authorization rules, where it's like only these particular users can express these facts. It's another gate. So if you learn about a fact, then let's check the structure of it. If it points back to a prior, then that prior conference has to be the same as this conference, and it runs that validation rule and then rejects it outright. But what would be even better is to build that constraint into the query. And now that we've got this idea of an implicit AND, we can do that. So we can have this other step in here. So we can say E prime dot P, see, this would be E prime dot S equal E dot S. So now we've got this this path, and since I'm starting with A and looking for those, then I would actually invert those. So now from A, I follow AR, and then follow S down to E. So now I've got AR equal ES gives me these, and then ES equal E prime S. So all of the others that point to this same subject here.
The same predecessor.
Yeah. And then where there does not exist this E prime, where the prior points back to E. So now I'm only looking at that subset. So I've done that intersection. And I'm not looking at any E primes that don't point back to the same successor, or the same predecessor S. And the way that I would express that in code is just like that.
Because if a fact would have as a predecessor a certain fact, the P pointer, but then goes to a complete different fact, it doesn't make any sense.
Right. Right.
So why would somebody do that? Just by mistake, or?
Yeah, it could be a mistake. It could be nefarious. And so I want to be able to express that constraint so that neither mistakes nor deliberate, an intentional attempt to break the system will be successful and would cause you to not see the result that you're expecting to see. So,
if we do that at that moment when we run a query, then it's in fact too late, because if I understand well, we should do that the moment that we add a fact to the system.
Yeah. Yeah, it might make sense to continue to do validation rules as well. Yeah, this is kind of going back to the diagram here. So here we've got the authorization rules on the server. So so we're not trusting the client. So that's kind of the idea that we're talking about here, that prevent these ill-defined facts from getting into the store. And so yeah, if we've got validation rules, they run at the same place. So they're authorized and they're validated before they're put into the database. So the and so I don't think that would be a bad thing to do. But there's also another place where we want to run authorization rules. So this is, the server doesn't trust the client, but neither should the client have to trust the server. So whenever it receives any new facts, then the client gets to run its own authorization rules. And so it very well could be that, and now even think about server-to-server communication. So you've built out the substrate. Yeah, and this is very much thinking about the blockchain model, thinking about the not the two generals problem, but the Byzantine generals problem. So with Byzantine generals, it's that the generals don't trust each other, and so you just want to make sure that if one defects, then the others can detect that defection, and it doesn't corrupt the whole system. So so the way in which one of these Byzantine generals here could defect is not running the authorization rules and not running the validation rules, and instead just giving you a whole bunch of invalid and unauthorized facts. And so that means that upon receipt, everybody has to run the authorization rules and the validation rules. So so this gives you another check. So let's suppose that you intend to put in this validation rule, that I'm not going to allow a conference name where its prior conference is different than this conference. You intended to do that, but maybe you forgot, and so some facts got into your store. Well, if you then put the validation rule in place, the validation doesn't apply to the facts that are already there. Maybe validation could. Authorization certainly can't, but maybe validation could. But here, if you then also do this check on query, then it doesn't matter that that the pool of facts has been corrupted. You're only going to get the valid ones when you run the query.
Yeah. In fact, you run your validation rules the moment that you execute the query.
Yeah. Yeah, so you don't have to trust the sea in which you're swimming. You just trust the results that you get out of it because you're running those rules. It would be nice to be able to run the authorization rules at the same time as well, but there are reasons that you can't do that, and that has to do with revocation. If you were to revoke somebody's access and then you ran the authorization rule at the query level, then their entire history is gone. You're not going to trust anything that they ever said in the past. So revocation is not commutative, unfortunately.
But with validation rules, yeah, if it was once valid, it should always be valid.
Yep.
Well, somebody can have the right now to add a fact. He doesn't have it later. And so you encounter a fact that has been added by somebody who doesn't have the right today, but he did in the past, and you say, okay, it's not authorized.
Right, exactly. Which could lead to inconsistency if you've got two different nodes that learn about things in a different order. So I learned about the revocation of your authorization before I learned about this fact, so I rejected it. But somebody else learned about them in the opposite order. They accepted it. That's an unfortunate consequence of authorizations. But yeah, unfortunately, that is the best that we can do. Anyway, so
facts have one big disadvantage.
Yeah.
The diagrams are quite abstract, and you really need to think to get through it.
Yeah, I'm hoping
at least in my mind, it takes some time to let it go in and to really understand it.
Yeah, that is true. I've noticed that in myself and in everybody that I've shared it with. It's just I know that I've spent enough time with it that it's sunk in. So all I can say is that it can sink in, but yeah, it does take time, and I'm hoping that with patterns like this, we'll actually be able to take these patterns and turn them into like a generic class that now you can apply, and you can say, okay, a conference has a name, and you just somehow express that in C#, and it generates all of this code here, and then anytime you say I want the conference name, it generates that code as well. So
yeah, but then then it goes automatic, but still the math behind it is still there.
Yes, exactly.
And if you want to know how it works, you still need to understand the graphs to let it sink down. There is no other way, I think.
No, I don't think so. Yeah, in correspondence, I did have the mutable keyword that generated that code for you. And actually, when my friend Russell recommended that I put in that capability, I fought him against it for a long time. But then I said, okay, fine, I'll put that in there. I'll see if that works out. Yeah, I never did like it, but I understood the need for it.
Yeah, but it's I mean, once you understand the patterns, just replacing the pattern by the mutable keyword is not really necessary.
Yeah. Yeah, it's just more typing.
Yeah. But if you have the mutable keyword, you cannot make that error again.
Yeah, that's true.
Yeah, that's the advantage. Yeah, if you give people freedom, you give them power.
Yes, indeed.
Let me think about that Cartesian product and how that works. it will get in, no problem.
Yeah, excellent. Yeah, I can only imagine, people that were, well, actually, I don't have to imagine. I was coding 20 years ago. So people who were trying to figure this stuff out 20 years ago and the tools that they had, the things that we have today, are so far beyond what we had back then. So it's conceivable that what is now taking us a lot of brain power to figure out in terms of facts and directed acyclic graphs, coders in 20 years, they're just going to be exposed to this right off the bat. They won't be exposed to assignment statements and update statements. Instead, this is what they'll be learning, and they'll be, yeah, this is easy. And then when somebody shows them an update statement, they're like, why would you want to do that? That's so complicated.
Who's still programming in assembly language today?
Yeah.
But if you see the step from assembly to today's C#, for example, it's a huge way we have come.
Yes.
That you can almost write programs in natural language.
Mm-hmm.
It's not yet that, but that you don't care about memory location anymore.
Well, I have heard about some demos of GPT-3 that actually are getting pretty close to that. So, but that's a topic for another day. We need to call it a day for now, so I can get in and stand up.
Have to. Okay, Michael, thank you very much. Next Monday, same time.
Same time, yes.
Okay. Thank you very much.
Thanks, Jan.
Bye-bye.